Hello friends, in this video let's solve another interesting problem which involves projectile motion and an inclined plane. So what is given to us is that there is an inclined plane at an angle whose angle of inclination is theta. Then a projectile is thrown from point O at speed v0. It is thrown horizontally, so v0 is horizontal, and the projectile lands at point A. Acceleration due to gravity is in the downward direction, obviously, and what we need to figure out is an expression for the range r, that is the distance between O and A. Let's work this out. For the analysis of this problem, let's choose the x-axis as in the direction of OA and y-axis as perpendicular. So x-axis as this, y-axis as this. X, y. This is the path of the projectile. R is the expression to be calculated. We know that x makes angle theta with the horizontal line. V0 is given to be horizontal in the horizontal direction, so this angle is theta. So we can derive a few things now. Let's look at the acceleration vector first. So acceleration vector is in the downward direction, g. This is the x-axis, and this is negative y-axis, but it's negative direction. And this angle theta, this angle is theta, so this angle is 90 minus theta, and hence this angle is theta. So the x component of the acceleration vector ax is g sine theta I cap, and the y component ay is minus g cos theta j cap. So the acceleration vector as a function of time is g sine theta I cap minus g cos theta j cap. Let's look at the initial value of the velocity vector. So let's calculate velocity vector at time t equals 0. Again, x-axis, y-axis, v0, theta. This is vx, this is vy. So velocity vector at time 0 is v0 cos theta I cap plus v0 sine theta j cap. Now we know that dvt by dt is a t. Hence, integration of dvt between 0 and t is integration of at dt between 0 and t. So this implies that vt minus v at 0 is, let's substitute the value of at from here. So g sine theta I minus g cos theta j, g sine theta I minus g cos theta j dt. And value of v0 can be substituted from here. So v0 cos theta I plus v0 sine theta j. So vt minus v0 cos theta I minus plus v0 sine theta j equals equals gt sine theta I minus gt cos theta j. And hence vt equals v0 cos theta plus gt sine theta I plus v0 sine theta minus gt cos theta j. Position vector r differentiated with respect to time is velocity vector, and hence integration of r dr from 0 to t equals integration of vt dt between 0 and t. So rt minus r0 is integration of v naught cos theta plus gt sine theta I plus v naught sine theta minus gt cos theta j dt. R0 is the zero vector, as we can see clearly that the object was launched from the origin. So the position vector at time 0 is zero vector. So left hand side is nothing but position vector at time t. Now this right hand side can be simplified as v naught cos theta I integral dt plus g sine theta I integral t dt plus v naught sine theta j integral dt minus g cos theta j integral t dt. This implies that RT is v naught cos theta t I plus this is t square by 2 and limits are t and 0, so this is half g t square sine theta I plus this one is v naught sine theta tj, and last one is half gt square cos theta j. Grouping together the terms along the I and j directions, we get RT as v naught cos theta t plus half gt square sine theta I and v naught sine theta t minus half gt square cos theta j. Now we need to calculate this distance. When the object reaches this point A, the y component of the position vector is 0. So at A, y t, this is y component of the position vector, so this is r y t is 0. So let's say the time at which the object reaches A is t1. Let t1 is time at which the projectile lands at A, therefore 0. So the magnitude is 0 as well, and hence this is the expression for yt, v naught sine theta t1 minus half g t1 square cos theta is 0. So this can be solved to obtain t1 equals 2 v naught by g tan theta. The other value of t1 would be 0, which would satisfy this equation, but that is obviously not the one we are interested in because that is the time when the object was at O. Alright, so now R is nothing but magnitude of x at t1. If t1 is the time when object lands at A, then x, the x component of the position vector at that time is the magnitude of that vector is simply r. That is what we are after. So we are very near to the solution. So now the x component of the position vector is given by this v naught cos theta t plus half gt square sine theta. So v naught cos theta t1 plus half gt square sine theta plus half gt1 square sine theta. So this is, we can substitute the value of t1 into this, so we get r equals v naught cos theta times 2v naught by g tan theta plus half g sine theta times t1 square, which is 4v naught square by g square tan square theta. This g and this 2 go away, this is 2, so r equals 2v naught square by g cos theta tan theta plus 2v naught square by g sine theta tan square theta. R is 2v naught square by g. We can take out tan theta as the common factor of the two terms. So this becomes cos theta plus sine theta tan theta. Now we can take a little bit of a side calculation. Cos theta plus sine theta tan theta is cos theta plus sine theta times sine theta upon cos theta. So this is cos theta plus sine square theta upon cos theta. This is cos square theta plus sine square theta upon cos theta. Numerator is 1, so this is 1 by cos theta is equal to secant of theta. So this implies that r equals 2v naught square by g tan theta sec theta. This is the final answer. Thank you.